Okay. So we start to study the big algebra, and yeah, the first subchapter of chapter 2.1 is going through quite a few of basics or basic operations and some definitions in matrix algebra. So you guys are familiar with the matrix A of a size m by n, and then here the capital letter is denoting the matrix, but the small lowercase a with the subscript of I comma j indicates, so for example, a 3 comma 2 means the third row and the second column, and then the intersecting rows and columns, and the corresponding entry is this guy, a 3 comma 2. Okay, and then if you remember how we changed the vector equation into matrix equation, we can more compactly represent the matrix by using the columns of these matrix A. Okay, and then the capital letter again is a matrix, and this boldface lowercase letter is representing a vector. Okay, then the new another definition is a diagonal entry, which is just diagonal entry along the diagonals of the matrix. Then another term called the diagonal matrix is the square matrix, okay, which has the same size of a row and columns. And then in the diagonal matrix, the non-diagonal entries are 0. So this is one example of a diagonal matrix. And then the easiest example of this diagonal matrix as a special case is just a identity matrix, right? And then, as you guys know, if we multiply this identity matrix with some other matrix, and then it doesn't change this matrix at all. Okay, and then also, both of them are diagonal matrix, but what about this? Is this diagonal matrix or not? No? Right. Because we are considering the square matrix, right? So if the matrix is not square, and then we cannot even say whether it's a diagonal matrix or not. Okay. And also we have a zero matrix where the matrix entries are all 0. And then if the two matrices are equal, then just like the vector case. So let me ask the question: 1, 3, 5, and 1, 3, minus 1. Are these vectors the same or not? Or are these equal or not? They are not equal, right? Because we are saying they are equal if each of these entries are exactly the same. So in the case of matrix, if the two matrices are equal, then every element should be the same. And then also, of course, the size should also be the same between the two matrices. So I'm not going to give you any entries in the vector, but by looking at the shape between these two vectors, which is a 3-dimensional and this is a 4-dimensional. So if the dimension of the vector or the size of a vector is different, and then we cannot even talk about whether they are the same or not. because they are already not equal because of the size difference. So matrix is the same. So if the matrix has this different size, and then we cannot even say whether they are equal matrix or not. Okay, then the summation between the two matrices. We just do the summation element-wise. Okay, so if we think about the matrix, the summation of these two, yeah, so you can easily answer that. So the resulting matrix will have a 5 and 0, 1 and 6, right? Okay, and then the scalar multiple of the matrix A can be represented as this. So again, the capital letter is representing a matrix, and the lowercase but the boldface letters are representing a vector, but just non-boldface and the lowercase, in that case, is representing a scalar. So yeah, so if we are given this matrix and the scalar multiple is -1 times this matrix, and then we just multiply this this scalar with every element in the matrix. Okay, and then there are a few theorems which seems to be quite trivial. So these are commutative law. And then in the case of a vector addition, we can change the order of the summation or the addition among the multiple matrices. And then here, if we add a 0 with the matrix A, and then we still have a 0. And here, this 0, is it a vector or scalar or matrix? So there are 3 choices. So what should that be? Is it a scalar, vector, matrix? Scalar, vector, matrix. You raised 2 times? Yeah, right. So it should be the matrix, because we can only define the addition between some matrix with some other entity only when that second entity is the same size of matrix. Okay, so these are also quite trivially understood. Okay, so let's get a little bit more interesting. So we consider the two matrices A and B, and then in the previous chapter, at the end of a previous chapter, we considered the matrix A as a transformation or the function or the mapping, right? So in this case of an expression, we considered it as a linear system or systems of an equation. And then also we considered this as this, some kind of function or linear transformation that maps x vector through the transformation matrix A. Okay, so that way we can view a particular matrix as a function, and then we consider a composite function. So something like something like this, right? So fx is x squared plus 5, and then gx is minus 2x, and then we plug this guy into here, right? So that way we obtain this. But it can be viewed as this: x is mapped into minus 2x, and then this guy is mapped into through this function, so g and f and so on, right? So we can define this composite functions using the two different matrices. So we first map the vector x into bx by using the matrix B, and then that is further mapped or transformed by this another vector by the multiplication by another matrix A. Okay. So in terms of a matrix multiplication, it can be written as this form, A and Bx, which means X is transformed through B first and then further through matrix A. Okay, and then, yeah, it seems to be quite trivial, but there is something that we have to think about. So the one thing that we have to think about is this. So in this case, so what is the definition of this composite function? So it is defined by this representation, by plugging this x by minus 2x. But that way, it's 4 times x squared plus 5. So in this manner, we can view this composite functions that is composed of 2 steps as just another single function, right? So we can do the same thing here. So although in this case it's a 2-step process of mapping first using B and then A, but this 2-step function can be viewed as 1-step function, a single function of mapping X with the new matrix A times B, right? And then let's look at some interesting aspects from this quite straightforward relationships. Okay, so let's first think about the size of these two matrices A and B. So if A was m by n, then what is the size, or what are these two spaces? So should it be m or n? So first, so the question is, what is the dimension of the domain of A? Or A is m by n. And so we have to think about the dimension of the input vector x. So it should be n. It's n to m. Okay, so it's n dimensional, then it's transformed with the m dimensional, and then this vector is so this was B, so we have to consider B first. So B is n times p, and then the input vector dimension is p, and then it should be n, and then it's further transformed with the matrix with the vector of dimension m. Okay, and so here let's consider the columns of B. So our matrix B, which is the first step of our transformation, is composed of these vectors B1 through BP. Okay, so B, if B was 3, 5, then it is some matrix like this. Then we consider each column, right, as B1 through B P, or B5 in this case, because P is 5. Okay, then the first transformation that we go through in this step, okay, is, yeah, of course, B times X, the vector X, and then from this matrix vector multiplication, we know it's a vector equation form, and then it's a linear combination of the columns of B using the linear combination coefficient of an X from which is found here. And then let's further consider this matrix, the transformation using A. And then A is applied on each term, right? Then we have this. So here, yeah, although it looked quite trivial, but we did one single trick, that we change the order between A and this scalar x. Okay, so it's like we have a b1, for example, and then x1 was this guy, scalar, right? And then x1 came from this vector x and the first entry of an x, right? And then we have a big matrix here that we call A, right? In this case, it is actually the same as switching the order between A and X. Right? So we did this trick. But can we do this all the time? So can we apply this trick in any cases? So if X was X was a kind of general matrix or vector, can we do the same trick, or can we change the order between A and X? It is not generally possible. So let's think about the size of a matrix. So suppose A was 5 times 3, and then X was something like 3, 2, which is one kind of a matrix, not just a scalar. Okay, and then these two matrices are multiplied because they have the same matching size here, and then the vector b1 here is having the size of 2 by 1, because it is a vector. If we view that as a matrix, and then this will be the vector dimension, but this part will always be 1 because we consider the column vector. So in this case, the reason why we can define this matrix vector multiplication is because those sizes are matching, right? But in this case, if we change the order between these two, it's suddenly 3, 2 matrix times 5, 3 matrix times 2, 1, right? So in this case, those two doesn't match, right? And so here, as we will see, one non-trivial aspect or the characteristic that this guy is not the same as this guy in general, right? So among the matrices and their multiplication, we cannot freely change the order. Okay, but the reason why we can change the order between this x and a is because this x is just a scalar, right? So in the case of scalar value, we can multiply it anywhere in the sequence, right? So we can either multiply it at the end or at first, in the first place, and so on. So scalar can move freely. So that's why we can change the order here. Okay. So we change these order here, and then we obtain this. Okay, so we have this, which is after going through the entire two-step process or two-step functions or transformation, right? Which is this guy, and then this guy is still this guy can be viewed as a vector equation, because if you think about the size, A is something like this, and then B1 is a vector, and so this guy will have some column vector. So for example, A was 5, 3, and then B1 should be 3-dimensional vector, right? So the resulting vector is 5, 1. And then this vector is this part. So we have a column vector here, and then another column vector here, and so on. And then still we have these kinds of linear combination weights, which are all scalars. And then they came from this x, right? The original input vector. Okay, and then this is just having the form of this x1 times a1 or v1, and then x2 times v2, and so on. And then you guys know this linear combination of a vector can be represented as a matrix which has the columns of v1 and v2 here. So this is our matrix, and then we collect x1 and x2 to form a vector x1 and x2, right? So that's the trick that we used between the transition of a vector equation and the matrix equation. Okay, so we do the same thing here. So we collect those columns into these matrix, and then the vectors x which came from those values. So we change it to matrix equation form. Okay, and then we view this process. After doing so, what we obtain is this single matrix. For example, let's call that matrix as C. And this C times the original input vector x. Okay, so this can be viewed as just a one step of a matrix transformation using single matrix C. And that single matrix C, the columns in this single matrix C will have the form of A times B1 and A times B2 and so on. Okay, and so this is our new C. And then the C will have this, and then this single step of a transformation will have some similar form to something called standard matrix. So standard matrix. So so in the previous chapter, so probably you guys studied hard. So you consider a linear transformation, and then you do not know the matrix A. But how can you fill up the values in matrix A? So you first think about the transformation output of this unit standard vector, right? So that was the first column and the second column and so on. Okay, so that became our columns in matrix A. But in this case, if we use composite functions and then consider this a single matrix C, and then if B1 and B2 was just standard unit vector of 1, 0, 0 and 0, 1, 0, 0 and so on, this one will be just a standard matrix that we just already know, right? But now, since we are dealing with the two-step of a matrix transformations, and so instead of using unit standard vector, we are using B1 and B2, and then the output of each of these functions will form the column of the matrix C. Okay, so instead of using unit standard vector, we are using B1 and B2 and so on. And what was these B1 and B2 and so on? So those vectors came from the first transformation that we used here, and then their columns. Okay. And then this B1 is actually the output of the linear transformation using B with E1, or B times 1, 0, 0, 0. So this becomes B1, and then the meaning of it is this. So it is almost the same thing as a standard matrix. So I'll give you B that has 3 columns, B1 and B2 and B3. And then what should be the matrix X? I mean the dimension of the matrix, dimension of a vector X. What is the dimension? What is the dimension? So I already drew here. So it has a three component, and also, yeah, it's all again the same thing, but it can be viewed as a linear combination of these 3 vectors using the linear combination coefficient of these 3 elements, right? So that's why we have a 3 linear combination weight in this representation. And then here, suppose our x was 1, 0, 0, which is the unit standard vector. And then what is the result? So it is B1, B2, and B3, and then the linear combination coefficient will be 1, 0, 0. And so it's just picking up the first column, right? Okay, so so here, so I describe this as, instead of using 1, 0, 0, 0 or this kind of standard unit vector, we are using the first column of matrix B. Okay, and that first column is actually the output of matrix B times E1, or this guy, matrix B times 1, 0, 0. In that case, the first column will be picked up by using the standard unit vector. And then 0, 1, 0, we are picking up the second vector, right? And then that vector is further transformed with the A. So the second vector, which is an output from 0, 1, 0, 0, and that is further transformed by A. So it's almost like standard matrix form. Okay, and then yeah, let's think about another kind of interesting question here. So A times B1 is just having the similar form that we are using, like A times X. So A times X. So in the previous case, yeah, so let's consider this. So A1, A2, A3 as our column, and then X1, X2, X3. So this is linear combination of columns of an A, right? So this itself is viewed as a linear combination of the columns of an A, right? And then we have another vector here that is also a linear combination of the columns of an A, but using different linear combination weights. So this part became different, right? So each of these columns in this matrix A times B, I mean, we are talking about the columns of A times B, and then each column here can be viewed as linear combination of the columns of an A. Okay, so it is something like this. So suppose A has a 3 column, A1 and A2, A3. Then B1 was 1, 1, 0. And then what is this guy? This guy will be the linear combination of A1 and A2 with the linear combination coefficient of 1, 1, 0, right? And then the second column in this A times B is, suppose that B2 was minus 1, 0, 1. And in that case, the resulting column here is a linear combination of this A1 and A3 with the coefficient of minus 1 and 1, right? So that way, using different ways, we are linearly combining the columns of an A to form each columns in here, okay? So here, the question that I wanted to ask is this. So you can think about the span of the columns of an A. So again, we think about the span of the columns of an A. So that was our possible space where B can live in order to have a solution, right? So B was belonging to the span of the columns of an A, and then we can say that we at least have a one solution. Okay, then let's think about the span of A times B. So the first question is the span of the columns of A and A times B. Are those two spans living in the same space? In other words, the linear combination of columns in A, and then the linear combination of columns of A times B. Are they the vectors from those two cases having the same, do they have the same dimensions or different dimensions? So again, we talk about the span of A and A times B. And so we want to compare between those two span space, okay? And then the first question is, are the vectors from those two spans are living in the same space? Yes or no? Okay, so suppose the dimension of the columns of an A was 5. So each of A1, A2, A3 had a dimension of 5. Okay? And then the span will be, of course, 5-dimensional vectors. Right? And then let's think about this. This column vectors in A times B. So it was still the linear combination of columns of an A. Right? So just like this. 1, 1, 0. If B1 was 1, 1, 0, and then this one will be the linear combination of A1 plus A2, right? And so the linear combinations of the columns of an A will still stay in the same dimensional space, right? And also, you can verify that by simplify the size of a matrix. So suppose A was 5 times 3, and then the column space or the span of columns will live in a 5-dimensional space. And then what about A times B? So A times B will be 5 times 3, and then 3 times something. For example, 3 times 4. And then still the resulting matrix will be 5 times 4, where the first number will not change, which means the number of rows or the dimension of the columns, right, it will be the same. Okay? Okay, so the first question was answered. So they are at least living in the same universe or same dimensional space. And then let's think about which one is bigger than the other. So the column space of A and A times B has some relationships. So span of the columns of A and A times B, which one do you think is better? Not better, bigger. So one will include entirely the other. Can anyone answer? I think it's the worst bonus point. I think it's quite an interesting question that I personally think. So again, the question is, so you initially have a 3-vector, A1, A2, A3 in matrix A, right? And then you consider its span. And then you now consider another set of vectors, and each vector is a linear combination of the original 3, right? So that's what this green vector means. Each green vector here, each green vector is a linear combination of the original 3 vectors in A, right? So far so good, right? And so you create the linear combinations using these 3 vectors, and then you consider the span of these. Okay? So will this span be bigger than the span of the original 3 vectors, or will this span of these be smaller than the span of the original vector? So A and A times B. The span of columns, which one is bigger? AB? A times B? A times B? A. A times B. Can anyone answer the reason from each side? So among those answered, A has a bigger span. What is the reason? Why do you guys think so? Again, bonus point. What about the other party? Other side. For those who thinks the span of AB is bigger than the span of A, why do you think so? Just because A times B is more.
One is not related to others, so it's one color is linear combination of the other, so it's small one.
So yeah, so I give the answer. So suppose we have A1 and A2 and A3, and then consider the span of it, and then we consider the linear combination of these 3, and it doesn't matter. So suppose we have a linear combination of these 3, and then generate it using different combination weights. We generated 4 different vectors using 4 different sets of linear combination weights, and then consider the span of it. And then the answer here is this span is smaller than the span of original 3 vector. So the answer is span of A, columns of an A is bigger than the span of A times B. So it's a little bit counterintuitive, but this composite function of A times B, the actual ranges. So all the possible solution, or all the possible y values, and the set of these possible y values are called range, right? And then that range, so this is exactly the same as a range of the transformation A and the range of A times B. So the range of this guy is bigger, or they can be equal, but in general, it cannot be bigger. And this is why, that is because, so suppose we have a three vectors originally in matrix A, and then consider the span. And then we consider another set of vectors that are just linear combinations of these three. Okay? And then each of these linear combinations will still be living in the span of the original three vectors. Right? So it's like linear combination of linear combination. That linear combination of linear combination is still be represented as linear combination of the original three vectors. Okay? But in unfortunate case, or if we get unlucky, our linear combinations of the three vectors were having, so the first vector was something like this through the linear combination of these two, and then the other was this, okay, and then the third one was just linear combination. The third one was just included in the span of these two, and then the fourth one was also still inside of the span of the first two. And in that case, using those vectors and then considering all the possible linear combinations, it will be just a part of the original span space. Okay, so I give you just one simple example. So this is A1 and A2 and A3, and B1, B was, so first of all, B will have a three components, right? So the first component will be 1, 0, 1, and then the second component was 1, 0, minus 1, and then the third component was 2, 0, minus, or 2, 0, 1, and then the fourth component was minus 1, 0, 2. Okay, so these are four examples of linear combination. And then still, each of these four vectors will not involve A2, right? So linear combinations of these four linear combinations will still have no A2, right? It will not contain this A2. So it's possible that some of the original vector and some of the original component may not be included in those linear combinations through B. So that's why the span of span of A times B is smaller, or it can be equal, smaller than the span of original matrix A. Any questions? Okay, then, to wrap up to this point, A times B. So if you compute the matrix multiplication, which is A times B, okay, in that case, this matrix, the first column is just A times the first column of B, right? And then the second column will be the entire matrix A times the second column B2, okay? So that's how we form this matrix A times B. Okay, so if we compute A times B, we just mechanically compute these two matrix multiplications. But let's view that column by column by using just what we just learned. So we first think about the columns in B, and then we have an A, and then we have the two columns in A, and then B1 is 4, 1, So it's a linear combination of these two columns by using 4 and 1 as a linear combination weight. And the resulting vector will form the first column of A times B. Then the second column is using different linear combination coefficient, 3 comma minus 2, by using the same vectors of the columns of an A, right? So that's how we form the second column. Okay, so we have these, then we collect them, and that's how we obtain A times B. Okay. Okay, and then, so why do we learn those things? So what is the meaning of these things? I mean, we already know how to compute the matrix multiplication of A times B, right? And why do we learn these kind of different perspectives? So these kind of perspective is a really critical part in the linear algebra. So you have to view the matrix multiplication as a kind of column, linear combinations of columns or linear combination of rows. Although we didn't talk about the linear combination of rows, but yeah, this kind of intuition or this kind of perspective will give a kind of high-level understanding, okay, by using just a vector as a unit. So you think of this matrix multiplication by using at a vector level instead of just a single entry level. So what I mean by single entry level is this. So what would you do when computing the matrix multiplication of A times B? Okay, so I'll do this computation just mechanically. So what is the first entry? How do you compute the first entry? It is the inner product between these and these, right? So it's like 8 and minus 8 plus 3, and so the value will be 11, right? Then let's move to the second entry. So how can we compute that? So it's like the same row and then using the second column in B, right? So we would compute the matrix multiplication in this manner, right? But in this case, it doesn't give you any insights about the meanings of the first and second and those columns in the resulting matrix. But from the previous, the insights that we learned in the previous slides, we know the first column is the linear combination of the original matrix A by using the linear combination coefficient of 4 and 1, right? And then what is the second column? So it's still a linear combination of the columns of an A, but using different linear combination coefficient, which is found in the second column of a matrix B. Okay? Okay, and then in the next chapter, probably in the next chapter, we view the linear combination of rows. I mean, another perspective of viewing still the same matrix multiplication of A times B as a view from the perspective of the linear combination of rows. Okay, so let's go through the second set of theorems. So if we have these, and then we have this relationships, which we call associative law. Then this is a distributive law, and specifically this is called the left distributive law, and then right distributive law, and then this guy. is also satisfied. So here, so we cannot switch freely between the different matrices in the multiplication. But here, the reason why we can change freely the position of R is because R is just a scalar, right? So in general, this guy has the size of this. So R is this small thing, and A is a big thing, and B is another big matrix, right? So in this case, importantly, looking at this third one, so we have A here, the same A, but we can just put the scalar in the second position and the matrix B. Okay, so that's still possible. Then, yeah, so this identity matrix will not change the matrix A. Okay, so we will not, we will basically skip the proof, but I encourage you guys to check out or follow the detail, follow closely the proof, okay? And the proof is actually utilizing what we learned in the previous slides, like the linear combination of the original matrix columns of an A, and then forming the columns in the resulting matrix. Okay, and then this is in general is not satisfied in terms of the size. In many cases, it's not defined because if A was 3 times 2 and then B was 3 times 5, and then if we switch the order between them, 2 times 5, then 3 times 2, it's not even defined, right? Okay, and then let me ask the question then. So at least you want to be able to define B times A, and then what is the matrix size of A and B to make this definition possible? So what can we say about the size of A and B in order to be able to define the size of B times A? So originally, A times B it can be defined because of the size match, right? So 2 and 2 here is the same. So that's why we can define the matrix multiplication, right? But we switch the order. In general, we see if this is not matching, and then it cannot be defined. And then how can we make this definition possible? In other words, yeah. Can anyone answer before I give you the answer? A should be? 네? 네. Yep. Good answer. So the student gave an answer like this. So if A was 3, 2, and then the B should have the exactly the size of a transposed matrix, or size of 2 by 3. Okay, so it is something like this. So 3 by 2 is like this, and then so this is one example where if the two matrices change it, and then still the matrix multiplication is defined. Okay, and that's quite obvious. Okay, so but in this case, still even when the matrix multiplication of B times A is still defined, but their actual values will not be the same. I mean, the multiplication is defined, but AB and BA, those two matrices will not simply be the same, right? So that is this fact that matrix multiplication is not commutative. Okay, so commutative law is not satisfied in the matrix multiplication. Okay, and then another interesting one is this guy. So suppose you are given this equation. A times B equals A times C. In that case, we have some kind of an instinct that we want to cancel A. Okay, so in this case, B and C will become the same, right? So if we can just cancel out the matrix A, and then we should be able to say B and C are the same. But in general, we cannot do this thing. Okay, so we cannot easily cancel the same matrix A. And this cancellation is only possible when matrix A is 1 to 1. Yeah, yeah, that is quite the right answer. And more formally, if A is invariable, so A has an inverse matrix, in that case, we can multiply A inverse on the left-hand side, and so A inverse times A will become identity matrix, and that's how we obtain the B only. Okay, so it's not about cancellation. So matrix is not directly cancelled, but through, the way of canceling or removing A is through multiplying another matrix, A inverse. Okay, so we can only cancel or remove A through the multiplication of A inverse. So in order to do that, A inverse should be first defined, right? Yeah, but we didn't talk about the inverse yet, but we will talk about the inverse in the right next chapter. Okay, so in general, matrix is not easily cancelled, and thus, as a special case, if AB was 0, so in general, this 0, which I drew quite wide as a kind of wide 0, this is a matrix, right? So if A was 3 times 2, B was 2 times 5, and then the resulting matrix will be 3 times 5, and then if it was 0, and then this 0 means 3 times 5 matrix. Okay, in that case, just like the previous case, we cannot easily cancel A or B, so that we obtain either A is 0 or B is 0. So we cannot obtain this conclusion. It's still having the same reason of not being able to cancel the matrix. Okay. So the fact that this is not true is you can make matrix A and B as non-zero matrix, and still you can create a zero matrix. Okay, and then here, so I came up with another interesting question based on what we learned in this today's lecture. So we consider still A times B. So suppose A has three columns: A1, A2, A3. Okay, and then we learned the resulting vector, and then the first column is the linear combination of these, right? And then using some linear combination coefficient of B, right, we form the first column. And then the second column is another linear combination of these three. Okay? Okay, so the question is this. So we want to make this matrix A times B as completely zero. In that case, the completely zero matrix should, of course, have 0 columns in every column, right? Every column should be 0, and that's how we can obtain the completely zero matrix. So every column should be 0, right? Now how can we make this column as 0? So of course, yeah, so B, we don't know the exact size of B, but we know each column will have how many entries? How many entries in each column of B? 3. Why? Because we have to have the same number of linear combination weights, right? Because we have 3 columns, and then we have three different linear combination weights. So that's why we have three-dimensional column vectors in B. Okay. Now, of course, yeah. So let's try to create this this vector as 0. Then, if these were 0, of course it will be 0, right? And so for the second column, we say, yeah, we set them as 0. And then the second column will also become 0. So that is really trivial and quite easy and not interesting case, right? To create completely 0 matrix as a times B, right? So if B was 0, and then regardless of what A is, A times B is 0, okay? Okay, and then now let's think about a little bit non-trivial case. And by saying non-trivial, I guess you guys will recall some non-trivial solution in the context of in the homogeneous linear system, right? So if A1, A2, A3 are linearly independent, linearly dependent, and then we can make some non-zero linear combination coefficients, and then still create the linear combination as completely 0 vector, right? And then suppose that vector was 1, minus 2, and 3, okay? So one non-trivial solution of A times X was 0, and so in this homogeneous linear system, the solution for X was 1, minus 2, and 3. So suppose that, let's assume that this was one of our solution for homogeneous linear system. And then this case, since those values are containing non-zero, and so this can be viewed as non-trivial solution. And also in this case, you guys know this case is saying that A1, A2, A3 are linearly dependent, right? So at least one vector can be represented as a linear combination of the other, right? So if you studied hard for the previous exam, you guys should understand this quite well. Okay, so suppose 1, minus 2, and 3 were our solution. Then I will simply put 1, minus 3, and 3 as 1, minus 2, and 3 as the first column in B. And then now we created 0 column in the first column of A times B. Okay? Okay, and then let's move on to second column, which will work as a linear combination weight to form this second vector. And then I'll just create, okay, so in this case, I can just safely set all zeros, and still the matrix B is not 0, right? So in that case, A and B are not 0, and still A times B is 0. Okay, or 1, minus 2, and 3, and then another possible solution for homogeneous linear system was something like, so if 1, minus 2, and 3 were one solution as a non-trivial solution, and then you guys know 2, minus 4, 6 will be another solution, right? It's quite trivial. So by using that, you will have also another non-trivial solution for homogeneous linear system. Or it is still possible that maybe 3, 5, and minus 1, which seems to be quite different vector from the first one, but still, when using this linear combination coefficient, it was still making the linear combination of A1, A2, A3 as 0. So suppose you have another different combination that can create the linear combination of A1, A2, A3 as 0. In that case, you can freely choose those vectors in one of these columns in B parts. Okay, so in this case, so our conclusion is when A times B is 0, but still A and B are not 0 matrices. So neither of them are 0. So both of them are non-zero matrix, and still you can create A times B as 0. Okay, and that's when, that is satisfied when the columns of A is linearly independent or dependent. So again, the question is, so you want to create a non-zero matrix A and B. So you want to make both A and B as non-zero, and then still A times B, we want to have A times B as 0. In that case, the columns of an A should be linearly independent or dependent? Dependent or independent? Why do you think it should be independent? Okay. So for those who think it should be linearly dependent, why do you think so? 네. 네. 그렇죠. 네. 지금 이거죠. So this is just the example that we are talking about, right? So we have to have a non-trivial solution in the place of columns of B, right? So if the columns of an A was linearly independent, then in order to create the 0 vector in the place here, so if the columns of an A was linearly independent, and then the only possible solution for B, which work as a linear combination of weight, okay, so those values should be all 0. There is no other choice, right? So in that case, B will be completely 0. Okay, so in order to make B as non-zero, the columns of an A should be linearly dependent. So yeah, you guys now understood when A times B is 0, but both A and B are non-zero, and this is when the columns of an A is linearly dependent. Okay, and so now moving on to the next slides, we talk about the powers. It's simply the number of matrix multiplication of the same matrix. Okay, so a to the power of k is defined as k times of a multiplication of matrix A. And in this case, so let me ask another similar question. So in order to be able to define A times A as matrix multiplication, what can we say about the size of a matrix A? So suppose A was m by n, and then the same A will have the size of an m by n. So this n and m should be the same, right? So m and n should be the same, and so matrix A should be the square matrix. So we only when A is a square matrix we can define A times A or A times A times A and so on. Okay, and then similar to something like 3 to the power of 0, it is defined as 1. Okay, so it's like multiplying, 0 times of a multiplication of something will be defined as 1. Similarly, the matrix is, 0 times of a matrix multiplication is defined identity matrix. And so when multiplying it with the matrix, the vector x, it will be just giving the same vector. Okay, so the next one is a transpose. So you guys know the transpose, the definition of the transpose. So 1, 5, 2, 3, 4 minus 1. So suppose this was matrix A. And then a transpose is, first of all, what is the size? So matrix A has the size of 3 by 2, and then A transpose will have the size of 2 by 3, right? 2 by 3, and then what is the first column? 1 and 2 and 4, right? So it's diagonally flipping this matrix, right? Okay, and so we will see some properties of this transpose. So transpose of transpose will come back to the original matrix, and then the summation of these two. So this transpose operator will satisfy the distributive law, and then this is one interesting kind of aspect or characteristic. So the matrix multiplication and its transpose will be the same as the reversed order of the individually transposed matrix. Okay. Okay, and then scalar multiple, will be also converted into this. Yeah, I think that's it for the first subchapter 2.1. Although I wish I could go a little bit further into the next chapter, but we continue the next time. Okay, so that's it for today. Thanks. 어떤 거요? 좋은 지적이에요. 분명을 아까 내가 말로만 해서 조금 수리하지 않았던 부분이 있었는데 어떻게 하냐면 요거 하나하나가 이 리니어 컨비네이션 오브 컬럼도 본 A잖아요. 그러면 걔네들의 또 스캔을 쓰면 그러니까 약간 이게 이렇게 되는 거예요. 그러니까 A1, A2, A3가 있어요. 얘네들의 첫 번째 컬럼이 리니어 컨비네이션 코에피션트인데 C1, A1. 그러니까 이거는 스케일러고 이건 벡터예요. C2, A2 플러스 C3, A3 이렇게 되고요. 그 다음에 또 있어요. 하나가 더. 이쪽에 하나 더 있죠. 얘는 이걸 C라 그랬으니까 예를 들면 D라 그럴게요. D1. 네, 그렇게 하면 이거를 그냥 다 여기에다가 또 리니어 컨비네이션 코에피션트 만약에 2를 곱하고 또 여기에다가 또 E1, E2를 곱해서 리니어 컨비네이션 또 만드는 거예요. 이걸 다 풀면 그냥 A1의 리니어 컨비네이션 코에피션트가 어떤 C1, D1, E1들의 어떤 그걸로 표현으로 나타내집니다. 그렇기 때문에 여전히 A1, B1, A1, A2, A3들의 리니어 컨비네이션들로 표현이 돼요. 그러니까 이게 이쪽에서 이쪽으로 간다는 건 성립이 되고 이쪽에서 반대로는 못 갈 수도 있다는 거는 아까 그 카운터 이그젬플에서 그런 특정한 어떤 예제에서는 모든 그 리니어 컨비네이션 못 나타내니까. 알겠어요? 네.
지각에서 출석했나?
출석 안 불렀어요. 네.
이거 콜롬이 콜롬보다 왜 더 큰 범위인지만 말하면
네, 그게 그러니까 그러니까 아까 또 똑같은 그건데 이제 우리가 요 세 개가 있어요. A1, A2, A3가 있고 그 다음에 이거의 리니어 컨비네이션이 뭐 예를 들면 한 4개가 있다고 쳐봐요. 그러면 얘네들은 그러니까 얘네들의 리니어 컨비네이션이에요. 그러니까 이제 그거를 그러니까 예를 들어서 그게 뭐 이거를 그래요. 그러니까 이렇게 C1에다가 그러니까 얘가 갖고 있는 리니어 컨비네이션 코에피션트 그 B1 컬럼에 있던 그 엘리먼트들을 뽑아서 C1이랑 A1, 그다음에 C2랑 A2 이렇게 되면 그다음에 C3랑 A3 좀 못 써서 미안하지만 이렇게 되죠. 또 얘는 예를 들면 또 똑같이 나타내 보자고요. 이게 C1, C2, C3가 아니라 예를 들면 D1, D2, D3라고 해보자고요. 그러면 우리는 얘네들의 스팬을 따지자면 이것들의 sum linear combination 또 얘가 이만큼 잔뜩 있죠. 그거에 또 sum linear combination 이렇게 더해지죠. 그러면 이거를 예를 들면 E1, E2라고 해봐요. 얘는 이제 D1, D2, D3 이렇게 되면 자 그러면 이렇게 되고 이렇게 돼서 A1끼리 묶을 수가 있어요. A1끼리 묶으면 이제 E1, C1 플러스 E2, D2, D1 이렇게 되죠. 그러면 이것도 그냥 하나의 숫자일 뿐이니까 결국은 이게 any number, 그러니까 span의 definition any number가 될 수가 있으니까 이건 기본적으로 이거의 span은 기본적으로는 A1, A2, A3의 리니어 컨비네이션으로 그냥 나타내시는 거예요. 그죠?
아, 네.
그러니까 이쪽에서는 이쪽으로 무조건 갈 수가 있어요. 근데 이쪽에서는 이쪽으로 못 갈 수도 있다는 거예요. 아까 그런 어떤 특정 예제에서는 그런 좀 약간 좀 불운한 경우에는 얘가 이거보다 더 작아지게 된다. 항상 작지는 않아.
네, 알겠습니다. 감사합니다.
안녕히 계세요.
네, 수고했어요. 네.